Hello everybody, welcome to my debut. I'm the half-drawn man and I plan to host a scientific channel. In the real world, I'm a PhD candidate doing my doctorate. Keeping the specifics of my topic aside, I'm an environmental researcher. Studying the environment, I can't help but notice things are not as they should be. So in this video, I'm going to share a little bit of what I've come to learn on my academic journey with you. Now, the environment I study is the Arctic, and on that note, the topic of this video, and the next one, is Arctic amplification. Which just means that while climate change is warming up our entire planet, the warming is amplified in the Arctic. If the warming is amplified in the Arctic, that means the Arctic is getting warmer faster than the rest of the globe. Here we will discuss why that is, what that means for the planet, and what that means for us, in a very simplified and basic way. Worry not though, I promise it's not all bad news, and this video series will end on a more bittersweet note rather than a depressing one. Thus, without further ado, let's begin. Keeping with the laid out plan I mentioned, let's cover what's causing Arctic amplification. The main contributors are positive and some negative feedback loops. What are those, you might ask? Well, a positive feedback loop amplifies changes. This tends to move a system from its stable state to an unstable state. And a good example of that is alcoholism. You start drinking excessively, you get addicted, and that results in you drinking even more. You went from a stable, mostly sober you to an unstable alcoholic you. And unless you do something about it, it will just keep getting worse. Conversely, a negative feedback loop tries to keep the system stable by dampening changes. A good example of a negative feedback loop is your thermoregulation. When you're cold, your body shivers, generating heat, which warms you, and reverts you back to a stable, not cold state. When you're warm, you sweat, and the liquid evaporates off your skin. It absorbs your bodily heat, once again, reverting you back to a stable, not warm state. Now hold up, you might be saying, how could a negative feedback loop that aims to stabilize the system be leading to Arctic amplification? I'll tell you, but before I do, let me quickly remind you how electromagnetic radiation works. Why? Because most warming is caused by the sun. So the one thing all these loops have in common is that they involve radiation absorbed from the sun. So radiation, not just light, generally travels as a wave, reasons for which are beyond the scope of this video, but do look it up if you don't know. The more energy the wave carries, the higher the amplitude. This gives us more energetic waves. But there's another way to increase the energy of radiation, and that is with frequency, which is the inverse of wavelength, literally how long the wave is. Thus, to sum up, to increase the energy of a wave, you either increase its amplitude or its frequency, i.e. decrease the length of the wave. Pay attention to how these waves look like in upcoming diagrams, and see if you can infer the energy of the wave based on how it's drawn. Now let's talk about the Planck feedback, named after a plank of wood. Just kidding, it's named after the German physicist Max Planck, who, in addition to contributing to various physics breakthroughs, did research on, you guessed it, electromagnetic radiation. If you look at yourself in a thermal or thermographic camera, you'll see this. Different parts of the body radiate different amounts of heat. What determines how much each part radiates? How warm each part is. Here we can see my torso radiating more heat than my wrist. That's because the torso houses deep organs like the liver and heart, which generate quite a bit of body heat. Similar to our bodies, if we looked at the whole of the Earth through a thermal camera, different parts of the Earth radiate away different amounts of heat. Again, based on how warm different locations are. Thus, areas around the equator radiate away more heat than the cold poles. So when the radiation from the sun hits the Earth and gets absorbed, the poles will radiate away less heat than the equator. So in a way, locally, more heat is entering the system than leaving in the Arctic, leading to an overall warming. Now hopefully I did not lose you there. It's a negative feedback loop that is trying to bring Earth to have the same temperature throughout. So in a way, it is stabilizing it. If you already guessed Planck feedback should also have a cooling effect elsewhere, you'd be right. Looking back at our diagram from before and focusing on the lower latitudes, locally, less heat is entering the system than leaving, producing an overall cooling effect. Of course, letting the Planck feedback reach its end goal, all locations will be receiving the same amount of radiation as they're radiating away back to space. But trust me when I say this, we do not want that to happen. Next, let's talk about a positive feedback loop, the ice-albedo feedback. Albedo means whiteness in Latin and is, in a way, a measure of how white things are. Why? Because white is reflected off of something if it is reflecting the whole color spectrum at you. And as these colors combine, your brain registers them as white. Ice being white reflects most of the incoming radiation from the sun. But as the Arctic gets warmer, there's less ice. Water, on the other hand, absorbs most of the red and infrared, so heat, and reflects, mostly, you guessed it, blue light. Now, since the Arctic is not a continent but rather an ocean, the water warming due to all this absorbed radiation translates to the Arctic warming. Interestingly, the effects of Arctic amplification actually happen during wintertime for this feedback loop, when the Arctic is experiencing its almost half a year-long night. During that time, the air is even colder than in summer, thus the only transfer of heat is from the ocean to the atmosphere. Reason for this being the second law of thermodynamics, but on a more simpler note, think warm things, when in contact with other things, make other things warm by dissipating heat that's stored within them. Unless, of course, there's a thermal insulator in between, which would keep the heat mostly contained. In our case, that insulator is ice and snow, and where there is no ice and snow, this transfer of heat is even stronger. To sum up, less ice means less albedo, which means more absorption, which means more warming, which means less ice. The last feedback we're going to talk about is the lapse rate feedback. Unfortunately, this one we will dumb down quite a bit due to its relative complexity, so I encourage all of you to research this further if you're interested to know more. Or comment down below that you want me to make a video just on the lapse rate feedback, and I'll get to it. Okay, so let's look at the situation in the tropics. So around the equator, you'll notice the tree line below, which should indicate to you that we're in the troposphere. The troposphere is just a lowermost level of the atmosphere that contains most of its overall mass. When the sun shines here, the shortwave radiation reaches the surface and gets absorbed. This warms the surface, increasing the temperature of the gas there. Mind you, temperature is the measure of average kinetic energy of the particles in a substance, which for our purposes can be shown by vigorously moving particles. As they move faster, they exert more pressure and increase the overall volume they occupy. The particles taking up more space lowers the density or degree of compactness of the gas. Now we have a colder, denser, and therefore heavier gas on top of warm, light gas. The warm air rises and the cool air descends, and through this cycle, all the heat is safely radiated back to space, cooling the tropics. Now, what was the feedback loop we just described? That's right, a negative one. Can you imagine an environment where this exact feedback loop would be positive? Spoiler alert, the Arctic is one such example. The troposphere in the Arctic is stratified, and stratified is a fancy way of saying layered, as a stratum is Latin for layer. Thus a stratified troposphere means there are distinct strata or layers that separate it. What am I trying to say here? Well, quite frankly, I'm telling you that the troposphere in the Arctic is an ogre, or an onion, or just a layered mass of gas with each layer from the ground lighter and with less particles than the one below it. In this ogre/onion environment, when the sun shines here, the surface absorbs the heat, much like in the tropics, but it is much harder to leave a stratum, as each stratum is like a separate system. And as a result, this surface layer in particular just keeps getting warmer and warmer. Warmer surface means more melted ice, which means more absorption, which means more surface warming, and there you have it, another positive feedback loop destabilizing the Arctic. Now, this is where we'll stop our scientific discussion. In the next video, we'll discuss what are some of the resulting effects of Arctic amplification, which should hopefully explain why the study of these feedback loops is important. Note, we did not discuss all feedback loops. The three we discussed are the ones that are most critical to the Arctic system, and are most relevant when it comes to amplified warming in the Arctic. There are many more that are destabilizing the planet as a whole. Now, quite a few of them are more effective at warming in the tropics. After all, both the Planck feedback and the lapse rate feedback, as we discussed, cool the tropics, and yet the tropics are also warming, albeit thankfully not as much as the Arctic. If you want me to also go through other feedbacks, all you gotta do is request it in the comment section. This is the first video, and I would like the viewers to help me shape the channel. Anywho, that's all I have to say in this video. Make sure to come for the second part of the video series to learn more on Arctic amplification. If you enjoyed this video, leave a like, and to know when exactly part 2 is dropping, I would heavily recommend subscribing. Last but not least, thanks so much for watching my very first video to the very end. See you next time, wonderful people.